Hello everyone, and welcome to my senior project presentation, Fixture Design for Composite Wheel Center. Just to give you a better idea what this presentation will be about, I prepared an agenda for you. First, we'll begin in the background, where I'll explain how this project began. Then I'll move on to my problem statement. From there, I'll describe the material that I used to create my part. After that, I'll go into the design requirements for fixtures. Then I'll cover a couple designs that I considered during the process. And then I'll cover my final design. From there, I'll talk a little bit about how carbon materials are machined. And finally, the results. At the beginning of this project, I was asked by Ken Gamble, one of the founders of Quattro Composites, if I'd be interested in designing a composite wheel for him. Of course, I jumped at the chance and we went from there. We considered many different possibilities as to what kind of wheel we'd like to do, but then ultimately decided that Cal Poly's SAE hybrid team had a nice, simple geometry that would be easy to replicate. You can see the wheel center sitting by itself in the upper right corner, and then if you follow the red arrow down, you can see it fully assembled to the chassis. The wheel center has 12 holes on the outside that mount it directly to the rim, while the inner 4 holes mount directly to the hub itself. SAE was happy to work with us, and they were especially excited that they were going to get lighter wheel centers that were more rigid. The exciting aspect of this project was that up until now, nobody had ever created a wheel center or any part of a wheel from this carbon material. The hope is that someday this technology can be used to make everyday cars better. Creating the carbon wheel center actually took 2 senior projects. The first part was done by my partner Trevor Hegling, who designed the compression mold to create the parts. In his design, Trevor was unable to add features such as the holes that mount the center to the rim or the holes that mount the center to the hub. He could not add these because of flow issues with the material. It would have left seams and other defects that would have compromised the structure of the wheel center. Therefore, all those features had to be added after the hub had been compression molded. The only way to make sure that these features could be correctly located was to design a fixture to hold the part while the features were being added. The material that we used for our project is called AMC 8590 and is made by Quantum Composites. It is also referred to as sheet molding compound. Sheet molding compound is a combination of chopped carbon fibers that are then mixed with a vinyl ester resin, which is then rolled into a sheet and stored into a freezer. It is stored in a freezer so that the resin does not cure. SMC is designed for use on complex geometries such as our wheel center that cannot be created using conventional carbon fiber techniques. It is unique in a way such that the material becomes very viscous when heated in a compression mold and is capable of flowing into tight cavities. Also worth noting is that there is no shrinkage involved during the compression molding process. This is great for fixture design because it means there will be less variation amongst parts since they'll be much more consistent in size. Next, we'll take a look at the design requirements for a fixture. There are 7 and each of them are crucial. However, the first 3 are the most important of the bunch, and for this project, location reigns. Location is especially important in our project because if any of the holes are out of spec, the part will become defective. Holding the part is somewhat difficult to do because there are drafts incorporated into its design. This can be overcome by using a clamping force that keeps the part down in the fixture. Having good support for the part is crucial because the large cutting forces generated between the carbon material and the cutter can potentially cause the part to move. Before I could begin to design the fixture, I had to first consider which surfaces on the part were most important. I determined that datums A, C, and B were of most value to keeping the part concentric and perpendicular to the surface of the hub. Datum A refers to the bottom surface of the part. This is a critical feature because the holes must be perpendicular to that surface in order for the bolts to fit through on the hub. Of all the other diameters in this part, C is the easiest to measure and grab a hold of and makes the most logical sense to choose as a datum. Datum B refers to the bolt pattern for which the hub mounts to the wheel center. This is an important datum because it is used to reference the outer holes that mount to the rim. Those outer holes must be as concentric as possible to the bolt pattern. So now we'll take a look at some of the fixture designs that I considered. The first of which was to simply put the part inside of a lathe. The lathe I chose was capable of finding the true center and keeping all the specified GD&T in check. The lathe turret, which can be seen inside of the red square, is capable of holding live tooling. The live tooling can come in while the part remains still and machine the holes. As ideal as the mill sounded, there were a couple of problems. For one, the chuck could not properly hold the part since the part is drafted. The draft would cause the vise to squeeze the part out. The second major problem with this mill in particular is that it only had one live tool in it. This would not have worked because the process requires multiple live tools to handle the different size diameter drills and cutters. The second design that I considered came from the mold itself. The bottom half of the mold would make an ideal fixture for machining the part because it would preserve the part's concentricity as well as keeping it clocked in the correct position. The problems, however, are that you cannot machine the countersinks into the front side of the part. They are a critical feature because they help center the wheel once put onto the hub. Last but not least is my final design and the design that I ended up choosing for my fixture. It's a set of soft jaws that holds the part face up so that it can be machined from the top. Each of the datums is satisfied with this design. The first datum, datum A, which happens to be the bottom surface of the part, corresponds to the surface that the red arrow is pointing to. This will help ensure that all of the holes are perpendicular to datum A. The second red arrow points to the surface that satisfies datum C. Datum C will help ensure that the part is concentric and centered in the vise. The green arrows all correspond to areas that will be pocketed out of the soft jaw. They'll provide enough clearance for the drill to drill through the part to ensure that the hole is all the way through. They'll also allow for chips, or the dust that will form, to be evacuated from the soft jaw. This next slide shows an exploded view of the entire assembly so that you can get a better visualization of what it'll actually look like. The two soft jaws close on each other, holding the part securely. The only foreseeable drawback is that one of the soft jaws is fixed. This means there's a potential for variance of hole location within the Y direction. Not shown in this picture, but designated by two green arrows, are the places where two toe clamps will be positioned. These toe clamps will help secure the part inside the soft jaws. The reason for the toe clamps is to prevent the part's draft from forcing the part out of the fixture or moving it in any way. Next, I'd like to mention some things about machining carbon materials. When fully cured, SMC is an incredibly tough material to machine, and so feeds and speeds must be adjusted to compensate. Higher speeds are used in order to account for the hardness of the material. With the increased speeds comes high amounts of friction and heat. These are minimized by reducing the feeds, as well as applying ample amounts of coolant. In most cases where carbon is being machined, the number one concern is delamination. SMC, however, will not delaminate. All of its carbon fibers are in random chopped orientation, whereas traditional carbon fiber is woven together and can easily pull apart when in contact with a cutter. I'll have more information for you on Friday about speeds and feeds after I've completed my project. Unfortunately, I don't have any results to share with you right now. I'm still waiting for some of the tooling to come in so that I can drill through the carbon centers. I'll have more for you Friday morning when we meet. I'd like to give a special thanks to Dan Waldorf and Ken Gamble for all their help with this project. They shared with me their knowledge, experience, and time, and for that I am truly grateful. Without them, this project would not have been possible. And thank you, IIB members, for taking the time to listen to this, and I look forward to meeting you on Friday.